In this video, we're going to calculate the mean and the variance of a negative binomial distribution. And for the negative binomial distribution, we assume an event has a probability P that it occurs. So the probability that we flip a head on a two-sided coin, the probability that we draw a king from a standard 52 deck, whatever the event is, the probability is P. And we want to observe the event R times. And the negative binomial distribution the goal is to find the probability that it will happen on the X observation. Now, very important is what is the domain for X? Does it start at R or does it start at 0? And this also affects the geometric distribution because it's a negative binomial distribution when R is equal to 1. And we're going to take the approach that Wikipedia did, and we're going to let X equal the number of observations past R observations. We have to observe R observations because we want to find, we want to see R events. So it could happen in the first R cases. So if we let X be a negative binomial with parameters R and P, then this probably mass function is this: f of X is equal to R plus X minus 1, choose X, P to the R, Q to the X, where Q is 1 minus P, and the domain is 0, 1, 2 to infinity. P is, of course, a probability, so it's between 0 and 1. Now, is it a PDF? So what we do is we take our probability mass function and sum it over all possible values from 0 to infinity. And since this P to the R is not indexed by X, we take it out of the sum and we sum this. Now, if we look at a few of these cases, so when X is 0, it's 1. When X is 2, it's this. When X, or 0, 1, 2, etc. But this is what's called a general binomial. And there's a general binomial theorem. I actually have a video called that describes how we go from here to here. So this right here is 1 minus Q raised to the minus R. And of course the P to the R comes down. Now 1 minus Q is actually P. So that's P to the minus R. And those are common, add them, so it's P to the 0, which is 1. So it is a PDF, probably or PMF, however you want to say it. You can also say it's a PDF of the discrete type as opposed to the probability density function of the continuous type. But more common, people say PMF, probably a mass function. So the mean is the expected value of X. So we take X times the PMF and then sum it over all possible values. Now the goal in most of this is to manipulate it so it looks like a PMF again, probably mass function. So notice when X is 0, this is 0. So we might as well start at 1. And from here, so that X actually cancels with one of those in the X factorial. And we multiply and divide by R to make this R factorial. We multiply by P and divide by P. So that's what the plus 1 and the minus 1 represents. And we pull out a Q to make that X minus 1. Now, an index is just, it's a dummy variable in a sense. So let's let Y equal X minus 1. So then when we make that change, so this is Y, so that's Y, this is Y, and then everything else stays the same. Now, the reason we do that is now that, well, it's actually, so here we add 0, so we add 1 and subtract 1, and then this piece right here looks like a negative binomial distribution. Instead of R, it's called R plus 1. So we could change that to R star, or R prime, and R prime, and then it looks exactly like this. And we know that it is a probably mass function, and so this sums to 1, and we're left with r times q divided by p. And that's the mean of a negative binomial distribution. So we want to find the variance, but the trick to doing that is first finding the second factorial moment. And the second factorial moment is you go x times x minus 1. So there's 2 terms, so it's the second factorial moment. So that means we take this times the probably mass function, sum it over all possible values. But notice when x is 0 and x is 1, the terms are 0, so we might as well start at 2. And then again, the goal is to trick this to make it look like another probably mass function summed over its domain, which sums to 1. So we start pulling out things. We pull out q squared, so then that's why there's minus 2. We multiply and divide by p squared, so that's this 2 and this 2. And these, we cancel 2 terms with this factorial, and then we multiply and divide by r times r plus 1, and that's why we get this r plus 1 factorial. And here we add and subtract 2, so we basically adding 0 to this so it doesn't change it. We do an index change, so let's let y equal minus 2, and then so there's a minus 2 here. And this is, we just write it in combinatorics again. And then this is a hypergeometric with a new parameter r plus 2, so you can call that r star. Well, anyway, this integrates to 1, and we're left with this stuff out here. So that's the second factorial moment. Now, the reason we do that is because to find the variance, this is the usual formula, expected value of x squared minus the mean squared. Well, for a negative binomial, this is actually sort of tough to find by itself. So what we do is we trick this expression. We add 0. We add the mean and subtract the mean. So we've added 0 to this expression. But what that does, it lets us group these into this, right? So this would be x squared minus x, and the mean, it's a linear operator, so we would get this back. And then this is the mean, which we calculated on the first page, and that's the mean. But we calculated the second factorial moment up here. So now we substitute in. The mean was this. We square the mean. We get a common denominator. Simplify to this. Q plus P is actually 1, right? Because this is 1 minus P. So we're left with RQ over P squared. And that's the variance. Well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like it and subscribe so you don't miss the next one. Thanks. Bye.